The ground beneath your feet is not as solid as it seems. Modern cities rest upon tectonic foundations forged by ancient planetary forces. By the end of this video, you will see every skyscraper and city street through an entirely new lens, understanding the hidden forces that dictate their fate. What forgotten cataclysms lie buried directly below our busiest intersections? And how do the slow movements of continents influence the stability of a single building? When you look at a city's skyline, what story do you think the ground beneath it is trying to tell? This planet keeps its autobiography written in stone. Every city is built upon a vast library of rock, a collection of chapters stacked one atop the other, each page preserving a moment from an ancient world. The science of reading this library is called stratigraphy, and it allows us to decipher the stories held within the ground. These layered sequences, or strata, tell tales of tropical seas that once teemed with life, of vast deserts swept by prehistoric winds, and of colossal ice sheets that ground the very continents down. The deep foundations of our urban centers are often anchored in bedrock formed during the great eras of Earth's history. The Paleozoic era, with its ancient swamps and the first life crawling onto land, the Mesozoic, dominated by dinosaurs, and the more recent Cenozoic, the age of mammals, have all left their distinct signatures in the stone. Scientists extract long cores of rock from deep below the surface, cylindrical records that act like a geological time machine. By analyzing these samples, they can reconstruct entire vanished environments, reading the layers like a book to understand that the place we now call a bustling metropolis was once a silent seabed or a frozen plain. This profound perspective reveals that our modern urban world is merely the latest, thinnest layer in a story millions of years in the making. It is a story of constant, dramatic transformation, setting the stage for the immense tectonic forces that literally shaped the ground we build upon. These drifting continental rafts are propelled by Earth's immense internal heat, a restless engine that constantly rearranges our planet's surface. This is the grand theory of plate tectonics, the master blueprint that explains the fundamental geological framework beneath our feet. Where these colossal plates meet, their interactions dictate the very nature of the ground upon which we build our greatest cities. Along transform boundaries, plates slide past one another, grinding and locking in a slow, titanic struggle. The San Andreas Fault is a classic example, a scar across California where the Pacific Plate moves north relative to the North American Plate. This lateral stress does not build mountains, but instead stores immense energy that is released in sudden, violent earthquakes, a constant and formidable challenge for engineers in San Francisco and Los Angeles. Then there are divergent boundaries where plates are pulling away from each other. In these zones, the Earth's crust stretches thin, creating deep rift valleys. The East African Rift is actively tearing a continent apart, a process that, over millions of years, may create a new ocean basin. Conversely, at convergent boundaries, plates collide. This colossal crash can push up the planet's most spectacular mountain ranges, like the Himalayas and the Andes, fundamentally defining a region's geography and climate for eons. Grasping these three fundamental movements is the key to unlocking a city's geological destiny. It explains why some urban centers live with the ever-present threat of earthquakes, while others face volcanic eruptions or the slow, steady uplift of new land. The ground beneath a city is not a random stage, but a direct result of these ancient, ongoing battles between continents. This leads us to a deeper question. How do these slow-motion planetary conflicts, unfolding over millions of years, suddenly make their presence known in the heart of a modern metropolis. These invisible seams in the Earth's crust form a hidden architecture directly beneath our urban centers. A single fault is not just a clean break, but a complex, branching network of fractures that can extend for hundreds of miles, weaving a web of subterranean weakness. Over decades and centuries, the immense tectonic plates slowly grind against each other, their motion locking these faults in place. Stress builds relentlessly, storing energy like a colossal spring being compressed. Then, in a matter of seconds, that energy is released. The ground convulses, and the landscape is remade in an instant. This is the dramatic reality for cities like Istanbul, which sits squarely atop the North Anatolian Fault, a massive fracture where the Eurasian and Anatolian plates slide past one another. Similarly, the Enriquillo Plantain Garden Fault lies in wait near Port-au-Prince, a stark reminder of how major population centers often develop directly along these dangerous, yet frequently overlooked geological features. Scientists who study these ancient cracks, a field known as paleoseismology, have made a startling discovery. Many of these faults have a pulse, a repeating cycle of buildup and release. By digging trenches across a fault line and examining the layers of sediment, they can read the history of past earthquakes like rings on a tree. This reveals that a fault that ruptured 300 years ago will likely rupture again, providing a crucial timetable for disaster. This data is not just academic, it forms the backbone of modern building codes and urban planning, dictating where hospitals can be built and how high a skyscraper can rise. But the challenge runs even deeper. A major fault system is never alone. A maze of smaller, secondary faults often branches out from the primary fracture, creating a labyrinth of unstable ground below a city's foundations. For engineers, this means the ground beneath a single neighborhood can have dramatically different properties, some areas stable bedrock and others shattered rock and loose sediment. Designing the foundation for a new bridge or a towering high-rise becomes a delicate dance with this hidden, unpredictable terrain. How do you build a city that can withstand the sudden, violent movement of ground you cannot fully see? The answer lies not in fighting the Earth's immense power, but in learning to move with it. The most powerful tectonic collisions are the ones you cannot see. Far beneath the coastal metropolises of the Pacific, from Tokyo to Seattle, a slow-motion descent is underway. This is the world of the subduction zone, where an oceanic plate, dense and heavy, plunges beneath a continental plate in a geological act of surrender. As the descending plate grinds deeper into the planet's mantle, it does more than just disappear. It sets in motion a chain of events that forges and threatens entire civilizations. The friction of this colossal meeting melts rock, feeding a line of volcanoes that parallels the coast. These fiery mountains, like those in the Cascades or the Andes, provide the incredible gift of rich, fertile soil, the very reason many of these regions became agricultural and population centers in the first place. But this bounty comes with a terrifying price. The same grinding process that builds the mountains also locks the plates together, storing unimaginable energy over centuries. When that lock finally breaks, the result is a megathrust earthquake, the most powerful type of seismic event on Earth. The Cascadia subduction zone, stretching from Northern California to British Columbia, is a perfect and sobering example. For over 300 years, it has been locked and silent, building up strain. Geologists know its history, written in the sand, of massive earthquakes and tsunamis that have struck the coast every few centuries. For the modern cities built along this shoreline, this means existing on a geological timer, one that is counting down to an event that will reshape the landscape in minutes. This deep earth process gives these coastal regions their unique and dual personality. a combination of immense natural wealth and profound geological peril, all dictated by the unseen battle happening dozens of miles beneath the city streets. While subduction zones consume entire plates, a different kind of tectonic force is at work, one that builds new worlds by tearing old ones apart. This is the continental dance of rift valleys, where the very fabric of a continent begins to stretch and split. Along these massive fracture systems, the ground is slowly being pulled in opposite directions, a process that may, over millions of years, create an entirely new ocean basin. The East African Rift System is this process in action, a colossal scar running down the continent where Africa is quite literally splitting in two. Major cities like Nairobi and Addis Ababa have grown within this actively extending plate, their skylines rising from a landscape that is geologically young and dynamically unstable. This rifting creates a unique set of conditions that directly shape urban life. The thinning crust allows magma to rise close to the surface, fueling volcanic activity that can both threaten and enrich the land. It also unleashes tremendous geothermal energy, a powerful and clean resource that can power entire cities, turning a tectonic liability into a modern advantage. The very structure of a rift valley, a long depression bounded by parallel faults, creates a distinct basin. Over time, these basins fill with sediment washed down from the surrounding highlands, creating deep, fertile soil. This natural bounty has always attracted human settlement, supporting agriculture that sustains massive populations. We can see the long-term legacy of this process in places like the Rhine Valley in Europe. Though its major rifting phase happened tens of millions of years ago, it left behind a sunken trough filled with incredibly rich sediment. This geological gift created one of the continent's most productive agricultural heartlands, which in turn supported the rise of major population centers and trade routes for centuries. For modern cities built in active rifts, this gradual extension presents a complex puzzle. The same fault-bounded basins that provide fertile ground and resources also create a fragmented underground. The ground beneath a city can be a jumble of solid rock, deep, loose sediment, and hidden fault lines, all shifting at different rates. Building a subway system, a dam, or a foundation for a tall building requires navigating this hidden, fractured landscape. The very process that creates the land also constantly challenges our ability to build upon it. This leads us to a crucial question. How does the slow, relentless accumulation of sediment, the very stuff that fills these rifts, ultimately determine the fate of a city above? This mountain-building engine operates on a timescale almost beyond human comprehension. It is the slow, relentless collision of entire continents, a force that can raise the highest peaks on Earth from a once flat plain. The most dramatic example happening right now is the ongoing crash between the Indian subcontinent and the massive Eurasian plate. This titanic shoving match, which began tens of millions of years ago and continues today, created the Himalayas and the Tibetan Plateau. But this is not just a story of ancient geology. It is a force that actively lifts entire cities. Kathmandu and Chengdu are not merely located near these growing mountains. They are being pushed skyward, millimeter by millimeter, year after year, riding on the crumpled edge of this continental wreck. This constant uplift is paired with frequent, devastating seismic activity, as the grinding plates constantly adjust, releasing pent-up energy in powerful earthquakes. The creation of these great mountain ranges does far more than just sculpt the skyline. These colossal rock walls become weather makers, dictating regional climate by blocking rain clouds and creating vast rain shadows on one side and drenching monsoon seasons on the other. They dictate the flow of every major river system, whose headwaters are born from their melting glaciers, providing the freshwater that sustains billions of people downstream. For urban civilizations, these mountains have always been a source of immense wealth, their folded depths rich with mineral resources like copper, iron, and gemstones that have funded empires and fueled industries for millennia. For a city planner or engineer, this legacy of mountain building presents a formidable challenge. The ground beneath these regions is not a simple, solid block. It is a chaotic jumble of folded, twisted, and fractured rock layers, a geological labyrinth created by immense compressional forces. Designing a highway tunnel through such terrain means navigating unpredictable weaknesses. Siting a dam requires understanding how water might seep through countless hidden cracks in the foundation. Even laying the foundation for a single apartment building means knowing whether you are building on solid, stable rock or a layer of shattered debris poised to slide. The influence of this mountain building force extends far beyond the foothills. Even cities in what are now considered geologically stable regions, like those in the interior of North America or Europe, rest upon the eroded roots of ancient mountain belts that formed hundreds of millions of years ago. The gentle hills that define a city's landscape, the specific type of bedrock that anchors its tallest skyscrapers, these are all the worn-down ghosts of colossal peaks that once rivaled the Himalayas. This reveals a profound connection between the deepest time and our most modern urban spaces, showing how the very bones of a city were forged in fires of planetary creation that have long since cooled. That same fire that builds mountains also creates the most fertile ground on Earth. Volcanoes are not just forces of destruction, they are planetary engines of creation, and some of our greatest cities have been built directly in their shadow. Think of Naples, nestled at the foot of the restless Vesuvius. Consider Mexico City, built upon the ancient lake beds encircled by volcanic peaks, or Quito, sprawling across a high valley in the Andes, a mountain range itself born of volcanic fury. These urban centers thrive because of the very processes that could one day threaten them. When a volcano erupts, it does more than just spew ash and lava. It enriches the soil, breaking down rock into minerals that create incredibly fertile farmland. This agricultural bounty has, for millennia, supported the dense populations that eventually grow into cities. The volcanic ground also provides a direct source of power. Geothermal energy, harnessed from the Earth's intense internal heat, offers a clean and reliable resource that can light up homes and power industries. Even the rock itself becomes a resource. The volcanic stone we call tuff and the ash have been used for centuries as building materials, creating the very fabric of these historic cities. But this gift comes with a constant, looming reminder of its source. The same subterranean plumbing system that brings heat and fertility also holds the potential for catastrophe. Urban planners in these regions face a unique and daunting challenge. They must constantly weigh the undeniable short-term benefits of rich soil and abundant resources against the long-term, cyclical risk of a major eruption. Directly below these cities lies a hidden world of magma chambers and complex networks of fractures. This volcanic basement creates a unique set of underground conditions. Groundwater can be heated to boiling, creating natural hot springs but also posing risks of steam explosions. The ground itself can be unstable, prone to subsidence as magma shifts deep below. The very heat that provides energy can also bake the rock, altering its strength and how it responds to the weight of massive structures. The most dramatic dangers are the eruptions themselves. A single event can unleash multiple threats simultaneously. Pyroclastic flows, which are superheated avalanches of gas, ash, and rock, can race down mountain slopes at hundreds of miles an hour, incinerating everything in their path. Then there are lahars, violent mudflows of volcanic debris and water that can bury entire valleys in concrete like sludge long after the main eruption has ended. This is the complex calculation of life on a volcanic foundation. A city's water supply, its building stability, its energy sources, and its very existence are all tied to the slumbering giant beneath it. The ground does not just provide a stage for the city, it is an active participant in its destiny, a partner that is both generous and perilously unpredictable. This leads us to wonder, if the ground can be so dynamic and alive with heat and movement, what happens when it is not solid at all, but a flowing, liquid landscape that cannot support the weight of our ambitions? The ground can move even where the maps show no fault lines. Far from the dramatic edges of tectonic plates, the vast, seemingly stable interiors of continents are constantly, imperceptibly shifting. This is the force of intraplate deformation, a slow-motion warping that affects cities thousands of miles from any obvious geological danger zone. Think of Chicago, its skyline anchored deep in ancient bedrock, or Moscow and Sydney, built upon what appear to be quiet, stable landmasses. These cities are not immune to the planet's restlessness. They experience gradual ground tilting, subtle uplift, and even occasional, surprising earthquakes, all born from forces within the plate itself. These stresses are transmitted across incredible distances, like a tremor running through a vast, solid table. The immense pressure building at a colliding plate boundary thousands of miles away can flex the entire continental plate, slowly reactivating ancient, deeply buried weaknesses. These are fossil faults, scars from mountain building events that happened hundreds of millions of years ago, now being gently prodded back to life. The ground is also constantly adjusting its own balance. This is isostasy, the geological principle of buoyancy. When massive ice sheets miles thick melted away at the end of the last ice age, the land beneath, once crushed downward, began to rebound, slowly rising like a mattress after a weight is lifted. This glacial rebound is still lifting cities like Chicago and Moscow today, millimeter by millimeter, a persistent, slow-motion echo of an ice age long past. North America has its own quiet version of a continental split, a less dramatic but geologically significant system of rifts and faults stretching from the Midwest down to the Gulf of Mexico. This network of ancient weaknesses, a sleeping counterpart to the active East African rift, subtly influences the land, guiding river paths and creating zones where the crust is just a little bit weaker. For urban planners and engineers, this subtle warping presents a unique long-term challenge. It means that the ground is never truly static. A century of slow, cumulative tilt can alter floodplain maps and affect the gradient of vital infrastructure like canals and pipelines. The potential for intraplate earthquakes, while rare, means that building codes in these supposedly safe regions cannot afford to be complacent. A fault that last moved 10,000 years ago can still rupture again. This deep understanding connects global tectonic processes directly to the local conditions of a city street, revealing that stability is always relative and that the planet's slow breath touches every foundation, no matter how far inland it may seem. A city can live with a fault line running directly beneath its foundations. These urban centers exist in a state of constant negotiation, their skylines a direct challenge to the immense forces locked in the ground below. Tokyo is a masterclass in this precarious balance. The entire metropolis sits at a complex tectonic crossroads, where the Philippine Sea Plate is diving beneath other plates in a violent subduction zone. This geological reality means the city does not simply experience occasional tremors. It faces the constant threat of a truly catastrophic megathrust earthquake. In response, Tokyo has become a living laboratory for seismic survival. Its building codes are among the most advanced in the world, requiring structures to sway and absorb energy rather than remain rigid. The city has vast, designated open spaces for evacuation, and its citizens participate in regular, comprehensive drills. Every aspect of urban life, from the design of furniture anchors to the protocols of public transportation, is infused with an awareness of the inevitable. This is not paranoia, it is a sophisticated adaptation to a permanent geological truth. On the other side of the Pacific, San Francisco tells a similar story of adaptation born from disaster. The devastating 1906 earthquake was a brutal lesson in the power of the San Andreas fault system. The city was not just shaken, it was burned, as the tremors ruptured gas lines and triggered fires that raged out of control. In the decades that followed, the city's rebuilding process became a blueprint for seismic urban planning. Engineers learned to account for the phenomenon of liquefaction, where solid ground can turn into a temporary liquid during intense shaking, and for lateral spreading, where land can slide toward bodies of water. Modern skyscrapers in San Francisco are now engineered with deep foundations and flexible frames, designed to ride out the waves of energy that travel through the earth. Then there is Istanbul, a city of immense history built directly astride the North Anatolian Fault. Here, the challenge is layered, involving the protection of ancient monuments alongside modern infrastructure. The city has embarked on massive projects to retrofit thousands of vulnerable buildings, strengthening them against future shocks. It has also developed an ambitious early warning system, using a network of sensors to detect the first, fast-moving tremors of a quake and provide precious seconds of warning to shut down critical systems. These cities and others like them reveal a profound truth about our relationship with the planet. They are not built in spite of the danger, but in a continuous, dynamic dialogue with it. Every updated building code, every reinforced historic wall, and every public siren is part of an ongoing conversation between human ambition and planetary power. This delicate balance forces us to ask, if the ground itself can be engineered, what other hidden landscapes lie beneath our cities, waiting to be understood? A cylindrical core of rock pulled from deep beneath a city street is more than just a sample, it is a time capsule. These long tubes of layered sediment, extracted by drills that penetrate hundreds of feet down, contain the entire pre-urban biography of a place. In cities like London, Cairo, and Beijing, the ground beneath the subway tunnels and sewer lines is a meticulously kept archive, composed of alternating bands of sand, clay, and dark organic peat. Each distinct layer tells a specific story. A thick band of sand speaks of an ancient river channel, its powerful currents carrying sediment from distant mountains. A layer of fine clay might mark the quiet, deep bottom of a long-vanished lake, and a seam of compressed plant material reveals a swampy delta teeming with prehistoric life. By reading this sequence, scientists can reconstruct a timeline of dramatic environmental shifts, tracing how a river changed its course over thousands of years, or how the sea level rose and fell, advancing and retreating from the land that would one day become a metropolis. This geological ledger is especially profound in deltaic cities like New Orleans and Shanghai. These urban centers are built upon the colossal, accumulated gifts of their rivers. Over millennia, the Mississippi and the Yangtze have carried unimaginable volumes of silt and sand from their vast watersheds, depositing them at their mouths to form new land. The cities themselves are quite literally standing on this historical record of erosion and deposition. But this same process that created the land also created a monumental engineering challenge. These deep stacks of sediment are not solid rock, they are loose, waterlogged, and compressible. Building a heavy skyscraper on such ground is like placing a weight on a giant, water-soaked sponge. The foundation slowly sinks as the water is squeezed out, a phenomenon known as subsidence. The very ground these cities rely upon is inherently unstable, a direct consequence of the sedimentary history that gave them life. These alternating layers of different materials also create a hidden, three-dimensional plumbing system beneath the city. A permeable layer of coarse sand can act as a fast-flowing underground river, an aquifer that provides vital freshwater. But this same layer can also become a conduit for contamination, spreading a chemical spill from an industrial site far and wide. Directly above or below that sandy layer might lie a thick band of impermeable clay, which acts as a natural seal, trapping pollutants or creating unstable, pressurized zones of water. This complex hydrogeological puzzle directly influences everything from the stability of a building's foundation to the safety of the drinking water supply. When an engineer plans a new tunnel, they must map these hidden layers to avoid causing a collapse or puncturing a confined aquifer. Understanding this subterranean architecture is not a luxury, it is a necessity for the city's survival and health. Ultimately, this sedimentary archive offers a crucial key to urban resilience. By deciphering the stories of past floods, ancient landslides, and shifting shorelines held within the rock, planners can make more informed decisions about the future. They can identify areas most vulnerable to liquefaction during an earthquake, or zones where the ground is naturally prone to sinking. This knowledge helps dictate where to build critical infrastructure like hospitals and schools, and how to design defenses against natural disasters. Every new core sample adds another page to this ongoing geological story, preserving a record of environmental change that would otherwise be paved over and lost forever. The ground beneath a city does not just hold it up, it holds the memories of the landscape that was and offers vital clues for the city that is yet to be. Beneath the shifting sands and layered sediments lies the true heart of a continent, a foundation of crystalline rock. This is the basement, the final, solid floor upon which everything else rests. For metropolises like Montreal, Johannesburg, and Helsinki, this is not a distant abstraction. Their tallest towers are anchored directly into this ancient stone, a bedrock forged in the planet's fiery youth. This deep foundation offers a gift of incredible stability, a platform seemingly immune to the sinking and shifting that plagues cities built on softer ground. Yet this same strength presents its own unique set of challenges. Excavating a subway line or a utility tunnel through this incredibly hard rock is a monumental task, requiring powerful machinery and immense effort, a constant reminder that the ground's most reliable layer is also its most stubborn. The age of this basement rock is almost beyond human scale. We are speaking of the Precambrian, a span of time covering the first 4 billion years of Earth's existence. The granite and gneiss beneath these cities can be over 3 billion years old. To stand on an outcropping in Helsinki is to touch a substance that formed before complex life populated the oceans, when the planet's atmosphere was a toxic mix of volcanic gases. This stone is not a single, simple layer. It is a complex archive of the planet's most violent formative events. Within its crystalline structure, you can find the ghosts of mountains that rose and were worn flat eons before the dinosaurs ever walked. It has been folded, melted, and recrystallized in multiple cycles of creation and destruction, each event leaving its own subtle fingerprint in the mineral fabric. This ancient, fractured foundation actively shapes the modern city above it in surprising ways. The complex network of cracks and fissures within the basement rock creates a hidden plumbing system for the entire region. These fractures can channel deep, pristine groundwater, creating vital aquifers, or they can act as conduits for scalding water from the Earth's interior, offering a source of geothermal power. The very same fracture patterns also dictate how the ground will shake during an earthquake. Seismic waves travel differently through solid, unbroken rock than they do through a maze of ancient cracks, meaning the stability of a skyscraper can depend on the precise fracture geometry of the bedrock 1,000 feet below its foundation. In some cities, this deep history is not hidden. Where glaciers scraped away the overlying soil during the last ice age, the basement rock lies exposed, bare and magnificent. It becomes part of the urban landscape itself. You can see it in the rugged cliffs of Montreal's Mount Royal, in the rocky outcrops that define parks in Helsinki, and in the very quarries that provided stone to build Johannesburg. In these places, the connection between the modern city and the most ancient chapters of planetary history is direct and tangible. The pavement of a city street runs right up to a rock surface that witnessed the dawn of the continents. This enduring foundation forces us to consider what other deep-time secrets are locked within the stone, not just below our cities, but within the very materials we use to build them. The very ground a city trusts for its stability can, in an instant, betray it. This is the phenomenon of liquefaction, a terrifying process where solid earth becomes a temporary liquid during the intense shaking of an earthquake. It occurs in areas of water-saturated, loose sediment, places where the spaces between sand grains are filled with water. Under normal conditions, the friction between these grains locks them together, creating a stable surface. But when seismic waves pass through, they violently shake this saturated soil. The sand grains are rearranged, and the water pressure between them surges, pushing them apart. In that moment, the ground loses its strength and behaves like a dense fluid, unable to support the weight of whatever is built upon it. The consequences are both surreal and devastating. Buildings do not simply crack, they can tilt and sink into the suddenly soupy ground, often while remaining eerily intact. Underground structures, like septic tanks or utility tunnels, can become buoyant and float upward, bursting through the surface in a grotesque inversion of the natural order. One of the most iconic examples comes from the 1964 Niigata earthquake in Japan, where footage captured multi-story apartment buildings leaning at impossible angles, as if they were sinking into a lake of invisible quicksand. This is not a rare event. Major urban centers built on river deltas, like large parts of San Francisco and Tokyo, or on former marshlands and reclaimed land, like areas of Christchurch, New Zealand, sit atop this hidden vulnerability. The very process that created their valuable flat land, the slow deposition of sand and silt by water, also primed it for this catastrophic failure. In the wake of such disasters, the science of geotechnical engineering has advanced dramatically. Understanding a city's liquefaction potential is now a cornerstone of urban planning in seismically active regions. Engineers use complex models to map the underground, identifying zones of sandy, waterlogged soil that could turn fluid. Where development is unavoidable in these vulnerable areas, we fight back with sophisticated ground improvement techniques. One method involves injecting a grout-like material into the ground to bind the soil particles together. Another, called vibrocompaction, uses large vibrating probes to densely pack the sand grains, reducing the space for water and increasing the soil's inherent strength. For a city like Tokyo, vast tracts of reclaimed land in its Bay Area have been systematically treated in this way, an immense, unseen project to solidify the city's foundation against future tremors. This ongoing battle against an invisible threat forces a profound question. How do you design a city for a ground that can, without warning, lose its very nature? A city drinks from a hidden sea, deep beneath the pavement and the subway tunnels, vast reservoirs of fresh water flow silently through porous layers of rock and sand. These are aquifers, the planet's secret subterranean oceans, and they are intimately tied to the fate of the urban landscapes above them. The Ogallala Aquifer stretches beneath the American Great Plains, its ancient waters supporting agriculture and cities across 8 states. On the other side of the world, the Great Artesian Basin underlies much of eastern Australia, a colossal source of water that has dictated settlement patterns for centuries. These hidden water worlds are not just passive resources, they are dynamic geological systems that actively interact with the city. The water pressure within the aquifer helps to buoy up the layers of sediment and rock above, providing a hidden support system for the very ground we build on. When a city draws too heavily from this deep well, it does more than just risk running out of water. It begins to alter the physical foundation of the city itself. The water that is pumped out from between the sand grains and rock fragments is not quickly replaced. Without that internal pressure, the microscopic pores in the aquifer collapse and the entire layer of ground compacts. The result is a slow, silent sinking of the land, a phenomenon known as subsidence. In Mexico City, a metropolis built on the soft bed of a drained lake, the relentless extraction of groundwater has caused parts of the city to sink by many feet over the past century. This is not a gentle, uniform settling. It is a destructive process that cracks building foundations, warps roads, and ruptures underground pipelines. In Bangkok, the same issue has dramatically changed the city's relationship with water, making low-lying areas vastly more vulnerable to flooding during the rainy season. The city is now fighting a two-front war against both rising water from the sea and a sinking foundation from below. Yet these aquifers are more than just water banks, they are also time capsules. The chemistry of the water trapped deep within an aquifer holds a detailed record of the planet's ancient climate. Scientists can analyze isotopes in the water to determine when and how it fell as rain, thousands or even millions of years ago, revealing patterns of wet and dry periods that shaped prehistoric ecosystems. This water is so old that it has been isolated from the surface world for millennia, creating a unique environment. Within these dark, pressurized realms, entire ecosystems of microscopic life have evolved in complete isolation. These extremophile microbes survive without sunlight, deriving energy from the rocks and minerals around them, offering a glimpse into the kind of life that might exist on other worlds. Managing these fragile, ancient systems is one of the great challenges of modern urban planning. It represents a critical junction where geology meets public policy. The decision to drill a new well or to limit industrial water use is not just about resource management. It is a direct intervention in the geological stability of the city. Every drop of water pumped from the depths has a tiny but cumulative effect on the ground beneath our feet. How do we balance the immediate needs of a thirsty metropolis with the long-term integrity of its very foundation? The answer requires listening to the silent story told by the hidden water, a story of past climates and of a ground that is far from solid. We are the newest and most powerful geological force on the planet. Our cities do not merely rest upon their foundations, they actively reshape them, creating a hybrid underground world where nature and human ambition are permanently entwined. This is the birth of urban geology, a new chapter in the planet's story written in concrete and steel. Cities like Boston and Singapore provide the most dramatic examples of this transformation. Vast tracts of their modern coastlines are not natural at all, but land built from the sea itself. For decades, massive dredging ships have scooped up sand and clay from the seafloor, pumping it ashore to create new ground. This process of land reclamation does not just add territory, it creates entirely new geological formations. The material itself is a jumbled, artificial mix, and it settles and compacts in ways that are entirely unpredictable compared to natural sediment. The ground beneath these new neighborhoods is a human-made landscape, and it behaves by its own unique rules. The transformation extends far deeper than the surface. A modern metropolis is a city of tunnels, subway systems carved through layers of rock and sediment, creating a labyrinthine network that fundamentally alters the underground environment. These massive concrete tubes act as new, artificial pathways for groundwater, diverting ancient flows and creating new ones. The heat generated by trains, people, and machinery raises the temperature of the surrounding earth, creating a distinct urban heat island deep below the streets. Even the immense weight of skyscrapers permanently changes the stress field of the bedrock below, a constant, heavy pressure that the planet had never felt before the rise of the city. This complex interplay creates a cascade of new challenges. When you reroute an underground river by building a tunnel, you can inadvertently drain the water table in one area and flood another. The heat from a subway can bake the surrounding clay, changing its physical properties and potentially destabilizing building foundations over time. The very act of driving piles for a foundation shatters the rock and soil, creating a permanent zone of weakness. We have moved beyond simply building on the geology. We are now actively engineering it, and the Earth is responding in ways we are only beginning to understand. This new reality demands a new kind of science. The concept of urban geology acknowledges that the ground beneath a city is no longer a purely natural system. It is a hybrid, a complex blend of the original rock and sediment, and the artificial materials and structures we have inserted into it. This hybrid system behaves in novel ways, forcing engineers and planners to think not just about the forces of nature, but about the long-term consequences of our own modifications. The challenge now is to design with this hybrid system in mind, to create foundations and infrastructures that work in harmony with the altered geology we have created. This represents a profound shift in our relationship with the planet, a move from passive inhabitants to active shapers of the very ground beneath our feet. What responsibilities do we bear for the geological legacies we are now creating? The skyline of a city is often a direct echo of the ground it stands upon. Tectonic forces that shaped the continents millions of years ago continue to write the weather report for our greatest urban centers. The connection is profound and direct. When two continents collide and push up a massive mountain range, they do more than create a beautiful backdrop. They fundamentally reroute the planet's atmospheric circulation. This is the rain-shadow effect in action. As moist air is forced up the windward side of a mountain, it cools and releases its water as rain or snow. By the time that air mass descends on the other side, it is dry. The result is a stark climatic divide. On one side of the Andes, you have cities like Lima, Peru, a metropolis in a near-rainless desert that survives on ingenious water management and runoff from high glaciers. On the other side of the same mountains, the climate is lush and tropical. The same dynamic plays out with the Himalayas, creating the high, dry plateau that cradles Lhasa. For these cities, their very existence is a daily negotiation with a water scarcity dictated by a mountain range that formed tens of millions of years ago. Their entire agricultural support system, and therefore their ability to feed their populations, hinges on understanding this ancient geological handshake. Tectonics also crafts the stage for maritime prosperity. Look at the spectacular natural harbors of San Francisco and Rio de Janeiro. These are not random coastal features. They are often the product of tectonic forces, like the subsidence of a block of land along a fault line, which allows the ocean to flood in and create a deep, protected bay. These geological gifts position these cities as global hubs for maritime trade, bringing wealth and cultural exchange. But the benefit is not just economic. The vast body of water acts as a giant thermal buffer, moderating the local climate. It keeps coastal cities cooler in the summer and warmer in the winter than their inland neighbors, creating a more temperate and energy-efficient environment for millions of people. The influence of plate tectonics on climate even extends to a global scale. Massive volcanic eruptions, fueled by the subduction of oceanic plates, can pump vast quantities of ash and sulfur dioxide high into the stratosphere. These particles can circle the globe, reflecting sunlight back into space and causing a temporary but significant cooling of the entire planet. While a single eruption is a short-term event, the cumulative effect of this tectonic activity over millions of years has played a major role in shaping the long-term climate cycles of Earth. Today, these deep geological influences are overlaid with a modern phenomenon, the urban heat island. The concrete, asphalt, and vast surfaces of a city absorb and radiate heat, making it significantly warmer than the surrounding countryside. This human-made microclimate interacts with the local geology in fascinating ways. A city built in a valley, a geological basin, can trap this hot air, exacerbating air pollution and heat-related illnesses. A coastal city's sea breeze, a gift of its tectonic setting, might be its only relief. Understanding these complex interactions, the ancient foundation and the modern overlay, is the key to urban resilience. Planners are now using this knowledge to design for a changing climate. They are creating green corridors to channel cool air from geologically formed river valleys, choosing building materials that mitigate heat based on the local rock types, and managing water resources with a deep respect for the rain shadows and aquifers that tectonics provided. The climate of a city is not just an atmospheric condition, it is a geological legacy. A city can be built upon a literal fortune. The very ground that supports its infrastructure often holds immense mineral wealth, creating a complex relationship between urban life and the resources buried deep beneath it. This geological capital has shaped the destinies of cities around the world. Johannesburg provides the most striking example, a metropolis that exists only because of the golden treasure beneath it. The city was founded directly atop the Witwatersrand Basin, one of the largest gold deposits ever discovered. The urban landscape itself, from the location of its downtown to the famous mine dumps that dot its periphery, is a direct physical manifestation of that subterranean wealth. The city's entire economic history and explosive growth were dictated by the slow, patient accumulation of gold in ancient riverbeds billions of years ago. This pattern repeats itself in other corners of the globe, though with different metals. Norilsk in Russia and Sudbury in Canada are industrial cities born from geological formations rich in nickel, copper, and platinum. These are not settlements that later discovered resources. They are communities that grew from the ground up around the mines themselves, their identities and economies forever tied to the extraction of the valuable ores beneath their foundations. But the relationship is not limited to solid minerals. Other urban centers sit atop reservoirs of oil and natural gas. The early 20th century oil boom in Los Angeles saw derricks sprouting in parking lots and even within the city limits, a stark illustration of energy extraction happening side by side with urban development. Similarly, Baku in Azerbaijan has a long history intertwined with the petroleum reserves below it, its fortune rising and falling with the flow of oil. Tapping into this geological capital is not a simple matter of digging a hole. The extraction process beneath an established city creates a unique set of challenges. Pumping oil or water from deep reservoirs can remove the internal pressure that helps support the layers of rock and sediment above, leading to ground subsidence. This slow sinking can warp roads, crack foundations, and damage underground utility lines. Mining operations, even those conducted deep underground, can destabilize the ground and risk contaminating the very aquifers that supply a city's drinking water with heavy metals and toxic chemicals. This creates an ongoing negotiation, a constant balancing act between the economic benefits of resource extraction and the preservation of urban quality of life and safety. How does a city manage its buried treasure without undermining the very ground it stands on? The answer requires a deep understanding of the urban subsurface, not just as a foundation, but as a bank account of geological resources that must be managed with extreme care for the city to thrive in the long term. We have learned to let the ground move without destroying what stands upon it. The most revolutionary idea in seismic engineering is not to resist an earthquake's force, but to outsmart it. This journey began with simple reinforcement, adding steel rods to concrete to give buildings a degree of flexibility. But the true breakthrough came when engineers stopped thinking about rigid anchors and started imagining structures that could float. This is the principle of base isolation. Picture a building separated from its foundation by a series of layered rubber and steel pads known as bearings. When the earth begins to heave and shake, these isolators absorb and dissipate the energy. The building atop them sways gently, almost floating on the seismic waves, while the ground below convulses violently. It is a dramatic decoupling of human habitat from planetary fury. The Transamerica Pyramid in San Francisco, completed in the early 1970s, was an early pioneer of this thinking, its deep foundation and tapered shape designed to sway, not shatter. Today, base isolation is the gold standard for critical infrastructure, from hospitals and fire stations to data centers, ensuring they remain operational precisely when they are needed most. This evolution in design was forged in the fires of disaster. Every major destructive earthquake, from the one that shattered San Francisco in 1906 to the Kobe earthquake in Japan in 1995, has served as a brutal but effective teacher. Each catastrophe revealed a new weakness, a new way that buildings could fail. In response, building codes were rewritten, becoming stricter and more sophisticated. This is not a one-time fix, but an ongoing conversation, a continuous feedback loop between the destructive power of the planet and the adaptive ingenuity of its inhabitants. Cities like Los Angeles and Tokyo have embraced this dialogue with immense retrofitting programs. They are not just building for the future, they are actively strengthening the past. Thousands of older, vulnerable structures, from concrete frame apartments to historic brick buildings, are being systematically upgraded. Steel frames are bolted into place, concrete walls are strengthened, and weak connections between floors and supports are fortified. This is a monumental, city-wide effort to renegotiate the safety of the existing urban landscape. Alongside base isolation, another technology has become commonplace: the seismic damper. These devices act like giant shock absorbers for buildings. Installed within a skyscraper's frame, they absorb the kinetic energy of an earthquake, converting it into small amounts of heat and preventing it from whipping the structure back and forth. Some use thick, viscous fluid, while others rely on the bending of heavy metal plates. The result is the same: a dramatic reduction in a building's violent sway, protecting both its structural skeleton and the people and contents inside. But the most advanced engineering is useless without a deep understanding of the local ground. This is where microzonation comes in. A city is not a uniform slab. Its ground varies from neighborhood to neighborhood. One area might be underlain by solid bedrock, which transmits seismic waves quickly but with less shaking. Another might be built on a deep basin of soft sediment, which can amplify the waves like a bowl of jello, dramatically intensifying the destruction. By creating detailed microzonation maps, geologists and engineers can pinpoint these hidden vulnerabilities. These maps directly guide development, determining where the strictest building codes must apply, where critical facilities should be located, and which areas might be better suited for parks than for high-density housing. This entire seismic design revolution is a testament to a profound shift in our relationship with the planet. We are no longer trying to conquer the ground, but to comprehend its language and move in rhythm with its power. We are learning to build dynamic structures for a dynamic Earth, creating a safe harbor within the storm of tectonic forces. A buried Roman street is more than a relic, it is a geological sentence. The ground beneath our oldest cities holds a double archive where the chronicle of human civilization is inseparably inscribed within the deeper chapters of the planet. In places like Rome, Istanbul, and Mexico City, you find a complex palimpsest, a manuscript where the ink of human history has been written, scraped away, and rewritten atop the parchment of the earth itself. The foundations of a modern building might cut through medieval trash pits, which rest upon the rubble of a classical temple, which itself was built over a layer of flood silt deposited by a long-vanished river. This is not just archaeology, it is urban stratigraphy, a record where every human action, from building a wall to discarding a pot, creates a new layer in the geological sequence. These cities are living libraries, and their oldest shelves contain stories that are both profoundly human and fundamentally planetary. The most dramatic examples occur when geological violence freezes a human moment in time. The eruption of Mount Vesuvius in the year 79 did not just destroy the Roman cities of Pompeii and Herculaneum, it preserved them. The volcanic ash that smothered the streets, homes, and people created a perfect, tragic cast of an entire society, a snapshot buried within a single geological event. Excavating these sites reveals more than just the artifacts of daily Roman life. It uncovers the physical evidence of the eruption itself. Geologists can study the layers of ash and pumice to understand the eruption's phases, its intensity, and its impact. This intertwining of the human and the geological allows us to reconstruct not only how these people lived, but also the precise planetary forces that ended their world. It is a stark reminder that urban fortunes have always been subject to the deep, restless power of the ground they are built upon. This layered record also holds quieter, slower stories. In Istanbul, archaeologists digging for a new metro station uncovered the ancient harbor of Theodosius, a bustling Byzantine port that had been completely silted up and buried over centuries. The layers told a clear story. At the bottom were the wooden pilings and sunken ships of the active harbor. Above that lay thick bands of sand and mud, sediment washed in from the surrounding hills, evidence of centuries of deforestation and erosion caused by a growing city. Finally, atop that were the foundations of later Ottoman buildings. The geological process of sedimentation did not just bury the harbor, it recorded the environmental history of the city itself, a history directly driven by human activity. A flood, an earthquake, a volcanic eruption, these events leave their own distinct signatures in the urban strata, creating a timeline where human history and natural history are bound together. Understanding this interwoven record is crucial for seeing our own cities clearly. When an archaeologist and a geologist work together to read these layers, they are not just uncovering the past, they are diagnosing the present. The same sediment that buried a Roman port might underlie a modern neighborhood, making it vulnerable to liquefaction. An ancient fault line discovered beneath an archaeological layer confirms that the ground has shaken before and will shake again. This deep historical perspective reveals that our modern urban challenges, from flooding to seismic risk, are not new. They are part of a long, dynamic conversation between human settlement and the planetary foundation it rests upon. By learning to read this double archive, we gain not just a window into the past, but a crucial guide for building a more resilient future, one that respects the deep stories told by the ground. This new vision for urban planning treats the ground as a living partner, not a passive stage. Cities in seismically active regions are deploying some of the most sophisticated early warning systems ever devised. These networks rely on a simple but brilliant fact about earthquakes. They emit two primary types of waves. The first to arrive are the P waves, which are fast but relatively weak. They are followed by the more destructive S waves, which travel slower but carry the real shaking power. A dense grid of sensors can detect the initial P waves and instantly calculate the epicenter and magnitude of the coming quake. This provides a precious window of time, sometimes only seconds, sometimes up to a minute, but it is enough for automated systems to perform life-saving actions. Trains can slow to a safe stop, elevator doors can open at the nearest floor, gas valves can shut, and surgeons in operating rooms can lift their scalpels from a patient. In cities like Tokyo and Mexico City, these alerts are broadcast directly to every smartphone, giving people a moment to drop, cover, and hold on. This technology represents a fundamental shift from merely surviving an earthquake to actively managing its impact as it happens. For coastal cities, the threat is not seconds but centuries. The challenge of rising sea levels is forcing planners to look deep into the geological past. By studying ancient shorelines, fossilized coral reefs, and sediment cores, scientists can reconstruct how sea levels have changed over thousands of years. This long-term perspective reveals that the current rise is not just a temporary fluctuation but part of a much larger, inexorable trend. This geological foresight is critical for designing defenses that are built to last. It is no longer enough to build a seawall based on today's tides. Engineers must now account for the combined effect of global sea level rise and local land subsidence, a sinking often caused by the very geological processes that formed the city's land in the first place. Cities like Venice and Bangkok are fighting this battle on two fronts, holding back the ocean while simultaneously managing the groundwater extraction that causes their foundations to sink. This holistic approach, where groundwater policy is directly linked to coastal defense, is a perfect example of geological urbanism in action. The core philosophy of geological urbanism is elegantly simple. A city should be shaped by its geology, not just placed upon it. This means using the natural topography as a guide for development. A valley formed by an ancient river might be preserved as a green corridor for floodwater and cool air rather than being paved over. A stable ridge of bedrock could be prioritized for high-density construction, while areas of soft, liquefiable sediment are designated for parks, sports fields, or other low-impact uses. This is not about avoiding challenges, but about intelligently aligning human ambition with planetary reality. It means understanding that a fault line is a permanent feature, so we design the infrastructure that crosses it to flex and survive. It means acknowledging that a delta will always want to sink and compact, so we build structures that can adapt or float. These forward-looking strategies mark a profound evolution in our relationship with the planet. We are moving from a mindset of domination to one of collaboration, from seeing the ground as an obstacle to be conquered to recognizing it as a dynamic system to be understood and respected. This deep geological wisdom is becoming the ultimate blueprint for creating cities that are not only safe and sustainable, but truly resilient for the long centuries to come. Beneath the city streets lies a second, inverted metropolis. This hidden world is a dense three-dimensional maze of subway tunnels, sewer pipes, fiber optic cables, and electrical conduits, all weaving through the ancient geology. Think of it as the city's circulatory system, a subterranean network that must constantly interact with the ground it occupies. The very rock and soil it passes through are not just a passive backdrop, they are an active participant in a complex, ongoing negotiation. In cities like Helsinki and Montreal, engineers have a powerful ally, the stable, ancient bedrock of the Canadian Shield. This incredibly hard granite allows for the excavation of vast, multi-level underground complexes, from shopping centers and swimming pools to data hubs and transit lines, all with minimal risk of collapse. The rock itself becomes the walls and ceiling of these spaces, a permanent and reliable foundation for the city's hidden life, but this advantage comes at a cost. Tunneling through such resilient rock is a slow, expensive process, requiring massive boring machines and immense energy, a constant reminder that the most stable ground is also the most stubborn to work with. Contrast this with a city like Amsterdam, built upon soft, waterlogged delta sediments. Here, the ground is a shifting, unstable medium. Every tunnel, every foundation must be carefully sealed and constantly monitored against the relentless pressure of groundwater. The famous canals are not just picturesque, they are a surface manifestation of a high water table that defines every underground project. Building a new subway line in such an environment is like trying to dig a trench in a saturated sponge, requiring complex techniques to freeze the ground or build watertight concrete boxes within massive excavated pits. The geology directly dictates the method, the cost, and the very feasibility of expanding the city downward. This intricate relationship influences even the most mundane decisions. The placement of a water main or a power cable is not arbitrary. Engineers must map the underground to avoid zones of fractured rock that could collapse, or layers of corrosive soil that might eat away at pipe walls over decades. A fiber optic cable might be routed through a stable layer of clay to protect it from vibrations, while a steam pipe could be placed in a sandier zone to allow for heat dissipation. Each utility occupies its own preferred stratum, a carefully chosen lane in the vertical highway beneath our feet. As cities grow denser and land becomes more scarce, this subsurface space has become a critically valuable and fiercely contested resource. We are no longer just building on the ground, we are carefully engineering a layered, three-dimensional city deep within the planet's crust. This creates a pressing new question. How do we manage this crowded, invisible landscape to prevent the conflicts brewing in the dark? From orbit, our planet's night side reveals a startling new geography. The constellations of light that mark our greatest cities are more than just patterns of human habitation. They are the signature of a new geological force. We have become planet shapers, moving mountains of earth and stone with an ambition that now rivals the great rivers and glaciers. The sheer volume of material we displace each year, the sand, gravel, and rock excavated for our foundations and skyscrapers, has surpassed the total sediment carried by all the world's rivers combined. This is not a metaphor. It is a measurable shift in the fundamental processes that shape the Earth's surface. Our urban centers are engines of geological change, creating entirely new kinds of landscapes that will leave a permanent mark on the planet. The most enduring legacy of this transformation will be the novel rocks we have manufactured. Think of the vast plains of asphalt that coat our cities, the artificial canyons lined with concrete, and the towering cliffs of steel and glass. These materials are not temporary. Concrete, when it hardens, becomes a synthetic stone, a dense, layered formation that will endure in the geological record for millions of years. Future geologists, if they exist, will be able to identify our urban strata just as clearly as we identify layers of limestone or sandstone today. They will find this strange, human-made rock filled with the chemical signatures of our industrial processes, and they will recognize it as the defining layer of a new planetary epoch. This is the core idea behind the Anthropocene, a proposed new chapter in Earth's history where human activity has become the dominant influence on the environment and geology. Our cities are the epicenters of this change. The decision to pave a wetland in Jakarta or to pump groundwater in Mexico City is no longer just a local issue. These actions are threads in a global tapestry of alteration, affecting atmospheric chemistry, ocean currents, and the very composition of the rock record. When we understand our cities as geological agents, it reframes everything. The concrete in a sidewalk, the steel in a bridge, the glass in a tower, these are not just building materials. They are part of a planetary scale transformation. The ground beneath a city is no longer just the ancient foundation we built upon. It is a hybrid system, a blend of the natural and the artificial that we are actively managing for better or worse. This perspective forces a profound question. What kind of geological legacy do we want to leave written in the stone of our planet? A silent pulse beats beneath the city streets, monitored by a nervous system of sensors embedded in the ground. This is the seismic monitoring revolution, where cities have learned to listen to their own foundations. In metropolises like Tokyo and Los Angeles, advanced networks of seismometers do more than just wait for the big one. They are constantly eavesdropping on the urban heartbeat, detecting a permanent, low hum of microseismic noise. This is the sound of the city itself, the vibration from millions of vehicle tires on pavement, the rumble of subway trains in their tunnels, and the deep thrum of industrial machinery. This background noise is not static, it is a rich data stream. By analyzing how these tiny vibrations travel through the ground, scientists can create a high-resolution, three-dimensional map of the subsurface. They can identify hidden faults, locate pockets of loose sediment, and distinguish solid bedrock from unstable, waterlogged soil, all without ever breaking ground. Now, a new technology is amplifying this ability 1,000-fold. It is called distributed acoustic sensing, and it turns something we already have, fiber optic cables, into a massive, ultra-sensitive ear. Each strand of glass in a telecommunications cable can act as a series of microscopic sensors. By firing pulses of light down the cable and measuring the tiny backscatter, engineers can detect minute strains and vibrations along its entire length. A single fiber optic line running beneath a city becomes a continuous seismic array, thousands of sensors in one. This provides an unprecedented street-by-street portrait of how the ground is moving. It can pinpoint the exact location where soil is beginning to shift, or detect the subtle precursors to a landslide on a crowded hillside long before it becomes visible on the surface. The data flowing from these networks is not just for academic curiosity, it is the lifeblood of urban resilience. It feeds into dynamic, living models of the city's geology that are constantly updated in real time. For emergency managers, this means that when an earthquake does strike, the shaking intensity can be mapped almost instantly. They can see which neighborhoods built on soft sediments are experiencing the worst amplification and dispatch resources accordingly. For urban planners, this deep listening provides a long-term forecast. It helps them understand how the slow, cumulative stress of urban activity, from groundwater pumping to the construction of new mega projects, is interacting with the ancient geological framework. This continuous conversation with the ground allows a city to not just react to disasters, but to anticipate them, designing a future that moves in rhythm with the planet's deep, restless power. A city's identity is literally carved from the ground it stands on. Look at the classic brownstone neighborhoods of New York. Their warm, ruddy facades are a direct expression of a specific geological layer, a Triassic sandstone quarried from regions like Connecticut and New Jersey. That distinct brownstone is more than a building material. It is the physical manifestation of a local environment from over 200 million years ago, now defining the character of a modern city block. Across the Atlantic, much of London's monumental architecture, from St. Paul's Cathedral to government buildings, is clad in Portland stone. This creamy white limestone, quarried from a specific Jurassic seam in southern England, is studded with tiny fossil shells, embedding the memory of an ancient tropical sea directly into the city's most important structures. These stones are not chosen by accident. They are a declaration, a way for a city to root its grandest ambitions in the very bedrock of its region. This deep connection often begins with a story. Long before modern geology, societies explained their origins through the dramatic landscapes they inhabited. The myth of Rome's founding is inextricably linked to its famous Seven Hills, a topography shaped by volcanic activity and the shifting course of the Tiber River. These hills were not just a backdrop, they were active characters in the city's origin story, providing defensive strongholds and a symbolic connection to the gods. Similarly, the city of Athens was defined by the Acropolis, a massive limestone rock rising abruptly from the Attic plain. This wasn't just a convenient fortress, it was a sacred rock, a gift from the gods that became the spiritual and cultural heart of a civilization, its temples built from the very stone upon which it stood. These foundation myths reveal a primal human instinct to weave our identity into the most permanent features of our landscape, transforming impersonal geology into a source of meaning and belonging. Even in our contemporary world, this relationship is preserved in the green lungs of our cities. Urban parks often serve as open-air geological museums. Central Park in New York is a masterpiece of this idea, where designers deliberately exposed the island's ancient bedrock, creating dramatic outcrops of Manhattan, schist that children climb and couples picnic upon. In Rio de Janeiro, the sheer granite peaks of Sugarloaf and Corcovado are not just scenic postcards, they are the foundational bones of the city, preserved within a sprawling urban national park. These are not accidents of landscaping, they are intentional preserves that allow millions of city dwellers to physically interact with the planetary foundation beneath their feet, offering a tangible, often subconscious, connection to the deep history of their home. This cultural dialogue between a city and its stone culminates in a powerful truth. The ground beneath a metropolis is more than just a physical platform or a source of building materials. It becomes an active ingredient in the city's soul. The choice to build with local bluestone in Melbourne or with a distinctive red brick made from London clay creates a visual and tactile harmony between the built environment and the natural one. Over centuries, this repeated use of local geology forges a unique aesthetic, a sense of place that is felt by every resident and visitor. It transforms the anonymous forces of plate tectonics and sediment deposition into a core part of civic heritage and pride. How does this deep-seated cultural relationship, this marriage of human spirit and planetary foundation, ultimately shape our vision for the future of our urban world? The ocean is rising and the ground is giving way. For the world's great coastal cities, this is not a distant future threat, but a present-day reality unfolding along their shorelines. The true danger is not just the global rise in sea level from melting ice and expanding warmer waters, but a local phenomenon happening right under their foundations. The land itself is sinking. This dual assault creates a relative sea level rise that is dramatically accelerating the vulnerability of urban centers from Jakarta to New Orleans. In these places, the water is not only climbing higher, the city is actively sinking lower, a combination that is rewriting the map of risk. This sinking, known as subsidence, is driven by a mix of ancient geological processes and modern human demand. In a delta city, the very ground is a deep accumulation of soft sediments, layers of silt, sand, and clay deposited over millennia by a great river. The weight of the city itself slowly squeezes this waterlogged ground, compacting the layers like a giant, wet sponge. But we are also actively pumping out the water from the tiny spaces between these sediment grains, draining the aquifers below to supply a thirsty metropolis. When that water is removed, the support it provided vanishes, and the ground collapses inward, sinking sometimes by several inches a year. This is a geological process we have unwittingly activated. The story of this sinking is not new. It is written in the very sediments beneath these cities. By extracting long cores of mud and sand from deep beneath a city's streets, scientists can read a detailed history of past sea levels. They can find layers of peat from ancient coastal marshes that were drowned as the ocean advanced, or bands of sand from old beach ridges that formed when the sea retreated. This geological archive reveals that sea levels have always fluctuated, but the current rate of change, combined with the rapid rate of human-induced subsidence, is unprecedented in the historical record. This deep time perspective is crucial. It tells us that the ground we built upon was never truly static, and that our interventions have accelerated a natural process to a dangerous degree. The response to this crisis must be as layered as the ground itself. A simple seawall is not enough when the land behind it is collapsing. Cities are now forced to develop adaptation strategies that address both the global climate trend and their unique local geology. For Jakarta, the situation became so dire that the government has committed to moving the national capital to a new location on a more stable island, a monumental decision driven by the impossible challenge of holding back the sea while the city sinks. Venice has built its massive Moat barrier system, a series of mobile gates designed to temporarily isolate its lagoon from the Adriatic Sea during high tides. Yet even this engineering marvel must contend with the city's perpetual slow descent into its own foundations. In New Orleans, the strategy involves a complex combination of rebuilt levees, restored coastal wetlands to act as natural buffers, and ambitious projects to redirect the silt of the Mississippi River to help rebuild the sinking delta. The ultimate challenge for urban resilience is to stop fighting the geology and start working with it. This means drastically reducing groundwater extraction to halt the sinking, and designing infrastructure that can live with water rather than simply keeping it out. It requires understanding that the fate of a coastal city is a story written in two languages, the global language of the atmosphere and the deeply local language of the ground beneath it. How can a city learn to float when its very foundation is dissolving? A single piece of granite in a city park contains a memory older than all of human history. To hold it is to touch a moment from a world without flowers, without dinosaurs, a time when the very continents were arranged in alien configurations. This is the deep time connection, the profound realization that the stage for our urban lives was set by planetary processes operating over hundreds of millions of years. The limestone that forms the foundation of St. Louis was once the muddy bottom of a shallow sea. its calm waters teeming with shelled creatures whose fossilized remains are now compacted into the rock that anchors the Gateway Arch. The sandstone bluffs overlooking the Mississippi River in Minneapolis are the petrified dunes of a vast prehistoric desert, their cross-bedded layers telling stories of ancient winds that blew across a barren landscape. These are not just interesting facts, they are the very reason these cities exist where they do. The river carved its path through soft sedimentary rock, and the cities grew at the fords and waterfalls where that geology dictated. Our urban world is nested inside a much older, slower story. The coal that powered the Industrial Revolution, enabling the growth of cities like Manchester and Pittsburgh, is the compressed remains of swamp forests from the Carboniferous period, a resource created 300 million years before the first steam engine. The oil that fuels our modern metropolis originated in the microscopic plankton of Jurassic seas, its energy a gift from a world of marine reptiles. We are literally burning ancient sunlight, consuming the geological past to power the urban present. This perspective does not diminish our achievements, but it reframes them entirely. It reveals that our sprawling cities, our networks of light and steel, are merely the latest, most fleeting layer in an epic that has been unfolding for 4.5 billion years. The ground we build upon has been a mountain range, an ocean trench, and a lava flow, and it will be transformed again long after our current urban structures have returned to dust. How does this change our relationship with the places we call home? Embracing this deep time context invites a more humble and adaptive form of urban planning. It encourages us to design not for a static Earth, but for a dynamic one. We are learning to build cities that can accommodate the gradual uplift of land, the slow sinking of a delta, or the inevitable return of seismic energy along a fault. This is not a surrender to fate, but a wise acknowledgement of the immense forces that will always have the final word. It asks us to consider what legacy our own urban layer will leave in the geological record, and to plan for a city that can gracefully become part of the planet's next chapter.